All right, let's get started. So yeah, we made it to the end of the semester. So this is the last planned lecture. Maybe if we have really a lot to cover, we could do actually an extra lecture on Friday just to do some more revision topics if that's of interest. But let's see how far we get today first. First of all, I wanted to just address one point about assignment 2. So there have been a couple of groups that are having sort of big arguments about their contribution percentages, and I just want to say a few things about what the contribution is intended to reflect and how it will be used, just to give you sort of ballpark figures, right? So the contribution mechanism exists primarily to compensate for the fact that not all teams have 3 people in them, right? So it's mainly intended to deal with the case where we have teams of 2 and teams of 3 and trying to sort of balance out workload versus marking. And the way that it works is that the contribution percentage gets translated into a scaling factor which is applied to the team mark for the team deliverables in order to create an individual mark for each person in the team. And because it's sort of designed with a team of 3 as a baseline, that means that a contribution of 1/3 means that your individual mark will equal the team mark, right? That's sort of where the unit lies, right? So in a team of 2, if you are 2 people and you do an even share, you would expect the contribution to be 50-50. And at a 50% contribution, you would only have to do about 2/3 of the whole sort of to get a team mark of 2/3 in order to get a full mark, right? At a contribution of, let's say, 2/3 or something like this. So this is a non-linear function at the top end. So at 2/3, you would have to get a team mark of slightly more than 50% in order to get a full, maximum mark, a maximum individual mark, right? So it's kind of a non-linear function that tails off at the upper end. So that's just a reference point that is good to keep in mind. What else was I going to say about that? The other thing is that there are no sort of set rules for what constitutes a contribution. It is whatever you think contributed in some way or another to the success or lack thereof of the team. It's not intended to be proportional to number of lines of code that is in the submission, or proportional to number of tasks done, or proportional to time spent, or really proportional to anything else. It is up to you to decide. The final point that I wanted to make about this, and which really only concerns those teams that are having difficulty with it, is that it is the responsibility of the team to come up with an allocation of contributions. So under no circumstances will we go in and decide a contribution allocation based on sort of what you have submitted. If a team cannot agree, then we'll put them through a systematic process to determine an allocation of contributions, but that process will be based on inputs from all team members, and those inputs will only be numbers, right? So again, we are not going to look at who did what, who said they did what, or anything like this, and determine something. It is the responsibility of the team. And for those teams who are having difficulty agreeing, I would say that this process that we will use as a last resort is really a last resort It is specifically designed to incentivize you to agree rather than to go through this process. It is not likely to be to anyone's advantage. But that's that. So hopefully we will sort of be fairly, actually, so that should remind you about another thing as well. So although the deadline for submission was Friday last week, if you want to update either contributions or statements of originality, feel free to do that during this week, okay? Because the compliance checks is checking that you had correctly formatted files in place before the submission deadline. But if you want to change the contents of the files, so, and this is not just contributions, but as I said, also statement of originality. If there was something that you copied from somewhere or even read somewhere and then sort of wrote your own derived solution from or anything like this, you should mention it in statement of originality, right? And we're giving you the chance to update that now during this week. If you forgot about something that you might have taken from somewhere, some web page you read, some nice algorithm on, remember that that should be mentioned in your statement of originality, and you can update that during this week. Okay, so that's that. Now, the purpose of this lecture is to talk a little bit about the final exam and to address a couple of topics and questions that people have posted on Piazza that they wanted us to talk about in more detail. So just a quick summary of the final exam. It's scheduled 9:30 a.m. on the 8th of November, which I believe is a Tuesday, if I haven't got that wrong. It's 3 hours long. The format in terms of the technical design, how it runs, is the same as the mid-sem, right? So it will be online. You will clone and pull your questions from exam GitLab. You will submit your answers by pushing to the exam GitLab. The exam is open book, which means that you can refer to any course material, any notes that you've made, any documentation you find anywhere. But it is individual, which means you must not communicate with anyone during the exam except for asking questions of the teaching staff on Piazza. So no other chance of communication. So in particular, of course, you're not allowed to post questions anywhere sort of online about specific exam problems. So the sort of preparation procedures, again, this is the same as we did for the mid-sem. We will, if we can, have the exam server up and running during this week so that you can clone your exam repository. It will contain essentially nothing at this point, just a template README file and nothing else. And then sometime towards the end of the week, on Friday probably, we will close access to the exam repo. And then at the start of the exam, open it again, and then you pull an update, which will then populate your clone of the exam repo with your actual questions to be solved. And then remember that you have to push whatever you complete in order to have it marked. So what will be marked at the end is just what is in the repo on the server after the exam is finished. Now, I should mention one other thing here. I know that some students have timetabling clashes at this time, so there will be an alternative time scheduled for those students. It's not that many, it's 15 students or something like this. So we have a list of people that we know have clashes, and they will be scheduled at a different time. The other thing I should say is that for students who have an EAP that grants additional time on exams, we will add that to the exam time, and we will probably add that by making the start earlier. So, but again, we'll inform everyone who we know has an EAP about modified start or possibly end, but most likely start time. All right. Again, you have a lot of details about the final exam on the course website. Actually, I should check that that web page is updated. There may be something that we have changed and not updated on the web page, but we'll probably repeat most of this information on Piazza as well. Again, same as with mid-sem, we're giving you the option to do self-invigilation. Would strongly recommend that you do it if you can. And again, this is something that you want to do during this week, is to test sort of your technical setup to make sure that this is working, as well as your access to the repo and your IDE setup and everything. So just to again repeat this, the idea of self-invigilation is that you record yourself during the exam, and then you keep that recording, and we don't want it. We don't want to see it, unless if we have a reason to doubt academic integrity. So we start an investigation. Then you have the option to submit that recording as sort of an evidence in your favor, right? But again, it's optional. And just a reminder that for a recording to be useful as an evidence in case of an academic integrity investigation, it has to show enough that we can make use of it. So it has to show the screen of the computer that you're working on at a readable resolution, so we can actually see what is happening there. It has to show you, and it has to have audible sound, so that basically we can see that it's you at the computer, not talking to anyone, not using any other devices that could potentially be used to communicate with anyone. And it has to cover the entire duration of the exam. So again, on this web page, on the course website, there is some tips and hints for how to set up and to do the self-recording. All right. So any questions on the practical parts here? Question back there somewhere? No? Okay. I thought I saw someone waving a hand, but all right. So a little bit more about what we're actually assessing. So essentially everything that we have covered in the course is accessible material. The only exception there is that the contents of the guest lectures, so that's the one on, guest lecture, the one on game AI and the one on memory management that Tony did, are accessible for 1140, but not for 1110 or 6710. But apart from sort of everything, there is, of course, there is a core of knowledge here that we hope that you have learned. And what I would say is the core is, well, it's basic programming. So it's things like writing algorithms, iterative, recursive. It's understanding how variable scope works, variable state, references, the difference between references or reference equality and object equality and so on. And to some extent also using the standard library. So we have covered and made, I think, fairly extensive use of the collections from the standard library. So you should be familiar with at least the commonly used parts of the standard library enough that you can use them effectively where they are useful. It's not that we're going to test you specifically on that, but it's something that we're assuming when we estimate how difficult the question is, right? So a question can be very easy to solve if you know the right tool to solve it, and can be very difficult to solve if you don't know the right tool and you're trying to rebuild the relevant tools from scratch. So we're sort of assuming that you have reasonable knowledge of the common parts of the standard library. The other important thing, of course, is object-oriented programming. So this means things like defining classes that extend other classes, inheritance, how polymorphism works, method dispatch, using nested classes, how you create new objects and how they get initialized is sometimes important. Also remember that we talked a little bit about Java's notion of object equality. So we have reference equality and object equality, where object equality can be defined in a class-specific way, and we have class-specific hash functions, or well, we have default hash function for every object in Java, but we can also implement a class-specific hash function, and there's a relationship between hashing and equality in that two objects that are equal must also hash to the same value, right? Another thing that we have talked a bit about is data structures of different kinds. So we looked at abstract data types, which in Java are typically specified in terms of interfaces, but what we were most interested in is the implementation behind the interface. So design choices in implementing data structures is another sort of piece of core knowledge here. I will say that complexity, even though we only covered it quite briefly towards the end, is one of the key considerations, one of the important sort of considerations in making those design choices. So although it's a small component, but it is a component of what I would say is core knowledge here. And the final bit is a little bit of sort of software development practice. We haven't, I think, we haven't covered design or software development processes in a great degree in this course, but at least we expect to have sort of effective use of the tools that are available. So Git and IDE, I guess, are the main ones. And again, this is the kind of thing that factors into the difficulty of a question, in that if it's something that is easy to do if you know how to use the IDE, then we consider it to be easy to do. And of course, testing. So writing good test cases, we would say, is also part of core knowledge. And I think we'll revisit at least that one a little bit today. So I'm not going to sort of nail down any specifics, but let's say that this core knowledge should make up maybe around at least 3/4 to 80% or something like this of the exam. And then there will be some bit, maybe it's 20, maybe it's only 10, that is other things that we have covered in the course. All right. So with that, we'll move on to some of the topics that people have asked me to address. So I think one thing that quite a few people were asking about is recursion, and sort of how to understand or how to use recursion, and why recursive algorithms work and how they work. So it's a bit of a tricky one to explain, but we'll run through a couple of examples of how it's used. But I would say that at least I think of recursion as a way of thinking about how to solve computational problems. And the basic idea of it is that when you're looking at a problem, a computational problem, and you think, well, if I only knew the answer to these subproblems, then I could easily compute the answer to this problem, right? Then if the subproblems are the same as the main problem, but on a different input, a different argument, a different part of a data structure or whatever it is, then you have a recursive case, right? Then it's a case where recursive thinking is useful. So just as an example, I think this question was asked on Piazza about the height method in a binary tree. So the height of a binary tree is defined as the maximum depth of any node, or equivalently we can say the longest path from the root to any leaf node. So how would we figure out what the height of a tree is? Well, if we think about this longest path, right? The longest path from the root to any leaf node is going to start at the root, and it's going to go either down the right branch or the left branch. So if we know what the height of the left and right branch is, of the subtrees at those branches, then of course the height of the tree is going to be whatever is the maximum of those plus 1, right? Because if we take the longest path, let's say it happens to be on the right, we have a longest path here that is k steps long, then the longest path in the tree as a whole is going to be k plus 1. Right? So this is an example of sort of, if we knew the answer recursively, what is the height of the subtrees on the left and right, then it would be easy to calculate the answer. So that's the sort of the core of a recursive idea for how to solve the problem. Now, when it comes to actually writing code, usually if you have a recursive idea, it's fairly straightforward to translate that into a recursive implementation, right? Because essentially you just insert recursive method calls everywhere where you think, this is where I want to know the solution to the subproblem. That doesn't mean you necessarily have to have a recursive implementation. In some cases, you can translate a recursive implementation or a recursive idea into an iterative implementation in a pretty straightforward way. Let's say bisection search in a sorted list or sorted array is an example, right? So the idea of bisection search is that you look at the element, you're searching for a particular element or something that has a greater than less than relation to a particular element. So you look at the one in the middle and you say, well, depending on whether what I'm searching for is smaller or bigger, the answer is either going to be on the left or on the right. And then you can think of this as recursively, if it's on one side, say left, you recursively then do a bisection search on the left. But that doesn't mean you have to implement that with a recursive call. You can just sort of do a loop where you keep track of what are the endpoints of the interval that you're currently searching in. And we saw that example in the lecture where we covered complexity. We used that iterative implementation of a recursive idea, I think. Or maybe we used a recursive implementation, actually. Anyway, both are possible. The other thing that can be very tricky about recursive implementations is sort of how to collect the results. If the result is something simple, like just a number, like in the example of the height of a binary tree, the result is just a number, and we just return a number, we calculate a new number from the recursively calculated numbers. That's pretty straightforward. But if the result of the recursive algorithm is something more complex, like for example, let's say it's a collection of things, we want to, and a very typical example, which I think we'll try to do one maybe, is enumeration. So if we want to enumerate all sort of combinations or something, or all permutations or something, then the result that we want to return is something fairly complex. It's like a list or a set of complex objects. So then there can be multiple ways of collecting all those things that you compute and returning them. But I think we'll try to run through an example or two and see different ways that we can do it. So in fact, let's do that now. Right, so someone did ask if we could have a look at this example from the, I think it's from semester 1 2020 exam, solving a Sudoku. This is a bit of a boring example, but we can try to do it anyway. So does everyone know how to solve a Sudoku, or what a Sudoku is and what the rules are? Does anyone not know? Well, at least no one admits to not knowing. So we're given a 9x9 grid which contains cells, and in each cell there should be a number. Some of them will already have numbers in them, some of them will be blank. And the goal is to complete the whole grid, to fill in a number in every cell such that it meets a number of constraints. And the constraints are that every row, every column, and every one of these sort of 3x3 subsquares should contain exactly the numbers 1 through 9 in some order, right? So here we are given a as input an two-dimensional int array, which is the grid that we want to solve, and we have to return a valid solution. Does it say what we should do if there is no solution? Doesn't say. So maybe just as return a valid solution for the given setup. So maybe it's actually only will be tested on things that have a solution. Yeah. So I suppose that there are sort of slightly different ways you can think about how you would go about solving a Sudoku, but the brute force idea is just trial and error, right? So you find a blank space, one that you need to fill in. You put a number in that blank space, and then you check, can I put this number? Does it break any of the constraints if I put this number here now? If not, you try that number, and then recursively, now you have a partially filled grid. It's just slightly more partially filled than before. It's got one more number in it, and then you just invoke the same procedure again, right? Which means you just find the next blank, you try something there. If it doesn't work, you have to return something that says, nah, that didn't work, which means that when we say that we try something, that means we put a number somewhere in a blank square, we recursively try to solve this puzzle. If it doesn't work, we have to change what we did there. So that means we have to erase that number and put a different number there. And if we have gone through all the possible numbers that we could have put into that square and none of them work, then we have to say, no, this puzzle is unsolvable, and we have to return some kind of failure value to say that we couldn't solve this one. So do we need to clone? Does it say anything? A valid solution for the given setup? Okay. Well, I don't know. Maybe we'll do a sub or not in public. Just make it static. Subsolve grid. So I'm not sure exactly what it says about cloning or versus modifying, but we'll just because this one is taking a copy of the input grid, I guess we'll just work on that copy, only modify the copy, and then return the copy at the end. So our little subsolver is going to look something like how do we do that? Okay, this is just pseudocode, right? Blank. So we're going to find a blank position in the grid, and then we're just going to do something like for int number equals 1, number less than or equal 9. We're going to do set. We're going to do something like what is it? Grid I and j. Maybe we should call them row and col. Just to I'm assuming this is row major, row col equals number. So we're going to write a number there. Then we're going to do something like is subsolve grid. So then we're going to maybe actually we should, if we're doing in place modification, we don't need to return the grid. So this is I guess this is one of those when I said the tricky bit is how you return the value from a recursive algorithm. So in some depending on what your algorithm is, but typically when your recursive algorithm runs, you will get the answer, the result that you're looking for, well, either when all the recursive calls have finished and come back to the top with something and you compute the final value, or you will find the answer that you're looking for somewhere at the bottom of the recursion. So you will go down in different recursive branches, and at the bottom you will find sort of an answer somewhere. And it could be either that so in this case, the Sudoku case, we're just looking for one particular answer. So we'll find that somewhere, if it exists. Or in some other cases, we might be looking for enumeration. So if we're doing some sort of enumeration, we're looking for all possible answers, which means we'll find an answer at every leaf node of the recursion. And then we somehow have to collect all of them together. So there's kind of roughly 2 ways that we can do this. Either we do the same as in the simple case and we just return values up, and if we need to aggregate them to collect, like for example if we're enumerating, we need to collect everything together, then every recursive the recursive procedure, wherever it calls multiple makes multiple recursive calls, will take all of the return values and somehow collect them together into some kind of collection structure. The other alternative is that we have some kind of mutable data structure, like a list or a set or whatever it is, that we add things to at the bottom nodes, right? And if we do that, then we don't need to necessarily return very much. We might return something anyway, or we might just return nothing and just say, well, we're going to do this recursive process at every leaf node in the recursion. We're going to add something to this collection that we're building, and at the end, when we return back up to the top, we know that the collection has been filled with all the values that it should have, right? So in this case, maybe what we'll do is that the subsolver only returns a Boolean. So it will return true if it found a solution, false if it didn't. And we'll just modify the grid, because the grid is an array, so it's a mutable data structure. We can modify the grid. And we will make sure that if we return false, so no solution exists, then we have not modified the grid, which means we'll have to undo any changes to the grid. So let's just write that down so we remember. Return true if solution found. In this case, grid is modified to the solution. Return false if no solution. In this case, grid should be unchanged. All right, so guess that fixes the question here. So we say Boolean result. So we try to solve the grid, and then we do, what do we do? If, so maybe we should call it something else. We call it success. If success, then we just return true, right? So because if the recursive call returned true, then we have successfully solved the puzzle, the grid has been filled in, all we have to do is report back that yes, this has been solved. Right. And otherwise, we're just going to go around the loop and try another number. Right. Now, in order to meet our invariant here, so let's start with what happens if we get to the end of the loop and we have not succeeded. Well, that means that this setup is not solvable. No solution exists. So in this case, we should return false, right? But in order to meet our contract that we wrote here, we also have to make sure that the grid is not changed at this point. So if we get to the bottom here and we return false, we have to reset that square in the grid that we started to modify to be blank again, because it was blank on input. Right? We haven't modified anything else, so it's enough to just reset that one. So we'll do something like grid for row and column equals 0. So 0 is being used to represent the blanks here. And then we return false. Okay. Now there's a couple of things that are missing here. In fact, there's one. Well, let's put that here. So in this one, we're never actually checking for validity, right? We never check anything. We're also not checking for termination. So there's a couple of things that we're missing here. So one thing we should have here is to do it the really simple way. We would just say, if row and column is, I don't know, something like this. So basically what we need to do is to check if there is no blank in the grid, if the grid is completely filled, then at this point, well, we either have a solution or we have something that cannot be solved. It depends on whether or not we have checked. So maybe we should do a separate, I think it's easier to do a separate one for that. So we might do something like if not has blank grid, then return is valid grid. So let's say that we have a method that checks if the current assignment to a grid is valid or not. If it breaks any of the constraints, then we would check that at the end. So if we have a completely filled grid, we check if it's valid. If it's valid, then we return true. If it's not valid, we return false. So we can just return the value of is valid, right? And because we haven't modified the grid at this point, there was nothing to change. We don't need to do anything to to undo the changes. And then we can go on to find the next blank, and then of course at this point there should be a blank because we have checked that there is. Now the other thing that we could do here is to say, we could say if is valid grid. So instead of waiting to check for validity only when we have completely filled the grid, we can check if our isValid method takes a partially filled grid and checks for validity, then we could do that already here. So whenever we put a number into a cell in the grid, we check, is it valid to have this number here? Then if it's not, there's no point in bothering with doing a recursive call to fill out the rest of them because the end result is never going to be valid, right? This is a property of the puzzle that if we break a rule somewhere, then we can't fix that breaking of the rule by adding in more numbers somewhere else. So that, I mean, that's an important property of the puzzle, which might not hold for every kind of puzzle or problem you want to solve. So to complete this into a working solution, we would have to actually implement these sort of helper methods. Has blank, find next blank is valid. I think that's going to be a little bit time consuming. I'm not sure we want to actually step through and do it. It's going to take up quite a lot of time. But just to see how the whole thing would work, we would do something like, well, again, Boolean, call it success, is subsolve partial, and then, well, we expect that the puzzle is solvable, so we will assert that we did succeed. If we fail, then it's because something was wrong, and then we'll just return the grid that has been filled in. Right. So that's kind of the skeleton of a recursive solution for this problem. So I wanted to look at a different recursive problem, just to illustrate some of these considerations in creating a recursive algorithm. So this one is from the same exam. This is another variant of question 1.3, I think, or maybe it's 1.2, where so this is an enumeration problem, right? So here we're given a set of items, and we want to return all, essentially all permutations of this set that meet some particular restrictions or conditions, right? So in the setup of the question, the set is a set of vegetables, and the lists or sequences that we want to return are crop rotations. So they're saying, you know, first season plant this, next season plant that, next season plant that. And the rules are that, let's see, we should see, where is a crop rotation is a sequence of vegetables, one crop per season. Any crop may be planted at most once. So every element of that set is going to appear at most once in the sequence. Note that we are also given the length of the sequence that we're looking for as a parameter. So we're not necessarily going to use all of them. Obviously, because of that restriction of use once, we cannot make sequences that are longer than the size of this input set, but we can be asked to make sequences that are shorter, right? And then we have a number of restrictions here, or rules, which is saying that the different vegetables are partitioned into 4 different classes, or sort of 4 different types, and the rules are if we have something of type legume, then it must be followed by brassica, right? So it says may only be followed by, and then brassica may only be followed by an allium, and then an allium may only be followed by a fruiting crop, and a fruiting crop may only be followed by a legume. So as you can see, there's a sort of cyclic pattern where it's going through these 4 different groups, and essentially we have to go from one group to the next, to the next, to the next, and then back to the first, right? So just to sort of, again, to illustrate, let's say that we want to we could start off here by ignoring all of these restrictions and just generating all permutations, just because it sort of might help us understand how we design a recursive solution, right? So let's say we're going to do a, doesn't matter if it's public, static set of list of vegetable all permutations, where again we have same inputs, set of vegetables, crops, and int length. So it's not actually all permutations, it's all permutations up to a given length. Right. Okay. So so how are we going to do this? So here we're saying that the method should return this set of lists. Okay, so in order to enumerate all permutations, what's the sort of general idea? It would be to pick some element from the set, and let's call it element first from the set. Find all permutations of set minus, how do you use set minus? Use this notation first. So then we find all permutations of all the other elements that are not, except for this one that we have already picked, right? And then prepend or append, doesn't really matter. Let's say prepend first to all of these permutations and repeat for every choice of first, right? So the idea being that we're going to take out of the set of elements, we'll just pick one to be the first, generate all permutations of the rest, add that one that is first onto those permutations, and repeat that for every choice of which one could be first. So this is kind of our idea. Now, in order to implement this, we need to pass some things around, right? So we might say, because we put a width length minus 1 there. So because we put a limit on length here, we'll need to adjust that in the recursive call as well, right? So so how would we go about implementing this? Well, okay, so we're going to pick our first. So I guess we'll just do a loop over the set. Call that one first in crops. So that's our first element that we're iterating over. And what are we going to do? We need a set without this one. We could perhaps delete it from the set. But again, if you're doing a recursive algorithm and you're modifying mutable structures that you're getting in or out, you need to be very careful to undo changes, right? So we could say something like crops, do we have remove? Remove first. So we remove that, and then we do something like or we call it subpermutations equals all permutations of crops, and then minus 1, something like that. And now subpermutations here, of course, is going to be a set of what we'll need to do is we need to have a set here to collect our results in. So I guess we'll do a set of list of vegetable, again call it result, which is a new, I guess, hash set. I don't think we need to specify that. Java should figure that out. So now we have a set of subpermutations, all the ones that start with this current value of first. So in order to actually add them to our set, we have to prepend the first element and add them to this set that we're collecting. So we're going to do something like for perm in, that's my Python showing through, subperms. Oh, sorry, we need to do a var there. We're going to do something like, so this, I mean, even though we haven't declared it, this subpermutation is going to be a list here of vegetables. So what we're going to do is something like add, can we add at an index, add at index 0 first, something like that. So that's going to insert this one that we had said was going to be first at the beginning of this list, right? Position 0, I think. And then we are going to do add this permutation, add this permutation that we have just created to our result set, right? And then we have to remember again if we modify the argument, we have to unmodify it at the end, right? So in fact we can do it right here so we don't forget. We go after the recursive call, we have to add back that first element, right? We took it away temporarily to do the recursive call, and then we have to add it back. Now that's that's the basics of it, and then at the end we'll just then return our result. Right. So that should generate all permutations. Now there is something missing here. What is it you always have to have when you do recursion? A base case, yes. So we have to have somewhere where the recursion stops. Now where should we stop? Well, given the specification here, we said we want to generate all permutations of a certain length for a given set of elements. So if the length is 0, then we should not be doing any recursive calls. If the set is empty, then we cannot pick a first element, so then we should also not be doing anything. So actually, I should say the 0 and empty is kind of an arbitrary thing. We could also stop at 1. The only difference there is sort of like, if we have a set with a single element, there is only one permutation, we could just return that one. If we have a length of 1, there is potentially more than one permutation, but it's we can just take all the elements in the set, and each one of them will be a permutation of length 1. Stopping at 0 just makes it a little bit more general, because it means we handle the case with n equals 0 or an empty set. So I guess we should, yeah, and I think it's also easier to implement actually. So maybe what we'll do is just say if the set is empty, oh, that's clever, it's figured out that that's what I want to write, or length is 0, then, well, what do we return in that case? So you might wonder, well, what is all possible permutations of an empty set, or all possible permutations of length 0? So philosophical considerations aside, in order to make the algorithm work, what we have to return is a set that contains an empty list, right? Why do we have to do that? Because otherwise the one case wouldn't work. So if you think about what the one case is going to do, it's going to take all the elements in the set, it's going to recursively call, get back a set of lists, and then add that first element to each one of them. So for that to actually return the result we want, we have to return a set that contains an empty list, because then this empty list will have the first element added to it. They will all be added to the set, the result set, and that should work. So what we need to do is something like our permutation is going to be an array list of vegetable, I guess. It doesn't matter if it's an array list or a linked list or what it is. We can use an array list, which is empty, and then we are going to return a hash set. Can we actually, maybe we need to create the set. I'm not sure if we can do that in the constructor. And so we're going to add that empty list to the set and return that set. Right. So that's the base case, and then the recursive implementation should work for the others. Now, because we haven't solved the problem, we can't run on any of the given tests, but we can do our own little test here. So let's say that we do can we create some vegetables? How do we create a vegetable? It has a name and a group. Okay, and the group is an enum. Okay. So I guess we'll create, what do we create? We need a new hash set of type vegetable, and we're going to add to it some new vegetables. Let's create, I don't know, carrot. I don't know what it is. New vegetable. Cabbage. I guess cabbage is a legume, maybe. And let's see. We have. How does the song go? Carrot, cabbage, broccoli. Broccoli, which I do know is a brassica. Oh, that's why it's not. Group brassica. There we go. All right. So result is we do all permutations of this set of size 1, let's say. And then we want to look at the result. Unfortunately, it's a bit complicated. We need to do some printing. So I guess we'll do something like for in result. We'll create a string joiner. Because it's good to have, and we'll do for x in oh, sorry, we need to declare those. We can call that declaring. We're gonna do j add x. Does it have a toString? Yep. So we'll do that. And or does it actually have a toString, or is that inherited? No, it does have a toString. Yeah. Right. And then we'll do print to string. Okay, so this should print all the permutations. If we're lucky, let's see, this is telling us there's a problem somewhere. Why is it complaining here? Is that fixed? Yep, okay. Alright, so we should be able to compile that. Where? Crap. So it's because it always insists on compiling everything, even not just the things we want to run. Alright, so we're going to have to comment out this half-finished Sudoku thingy. We'll do that. Now that should compile. Alright, so back to our enumeration. Let's run that and see what happens. Oh, stuff goes wrong. What went wrong? Can we hash iterate the next node? Alright, now why is that not working? So this is happening in here where we're iterating over this. Why is that not working? It's non-empty. We should be able to iterate. Within the for loop we're modifying. Yeah, I figured it would be something like this. So we're not allowed to do that loop and modify it inside. So let's see if we can solve that. Can we do something like that? Can we do a clone? No. Alright. So this is a bit ugly. I'm sure there is a nicer solution, but we're just going to do this because it would be quicker than looking up what the nicer solution is. So we're just going to create a subset, and then we're going to do for other in crops if other is not first, subset add other. So that's just creating a subset that can, and adding to the subset everything that is not the one we wanted to remove. There may very well be a better way to do that, but we'll try that one just to see if it works. Alright, so that gave us 3 different permutations, which is kind of what we would expect because we asked for permutations of length 1 from a set of 3, right? So we changed that to 2, length 2, and we run that one again. Actually, is that running the tests or the main? I'm not sure which one it is. Then we get, what do we get here? We get 6 different permutations, and you can sort of you can manually verify that these are all the ones we should have, right? This is what you expect. So we have carrot followed by 2 other options. We have broccoli followed by 2 other options. We have cabbage followed by 2 other options, and so on. And of course, we can increase that to 3. Again, I think we need to run this one. All right. And did we get everything we should here? Yeah, we get the same. Like we get 6 again, because once we have fixed the first 2, there is only 1 remaining option for the last one. So we just get the same number. Of course, we can see what happens if we put 4 there. I don't know if we have actually considered that case. Yeah, it still works. I guess that works because we checked both if the set is empty and the length is 0. Right. So not sure how much more time we should spend on this example, but let's say that let's redo this example just to show a different way of doing a recursive implementation. That just where we again, so this is about how we collect the results of the recursion. So here we just had a function, it returns stuff, and we take all the return values and we collect them into a joint return value from the method. Right? But as I said, another alternative is to have some kind of mutable data structure and to just add to it whenever we find a new element that we should add to it. Right. So so in order to do that, we're going to have a I guess another static method, and actually this one doesn't need to return anything. Let's call it all permutations subroutine or something like this. So this one is going to take as input, well, we're not exactly sure what, something, definitely a length, a remaining length to fill in, and a set of lists of vegetables result. So in this one, we're going to do something, and every time we get sort of to the point where we have found a new permutation that we want to add, we're just going to add it to the result. And then the method doesn't need to return anything. So in order to do that, we need to recursively build up the lists that we want to add. So we might actually have to pass a list of vegetable, call it current or something like this. So that's the permutation that is currently under construction, we can think of. And of course we need something, the set of options. Maybe we can do something cleverer here. Right. Well, I don't know. Alright, we'll just pass the set there anyway. So we pass in the set that we have to choose from, we pass in the length, and so on. So so the idea here is that current is a permutation under construction. Now if the set if the set is empty or length is 0, then actually no, it's not if length is 0. Let's say current size equals length. Then then it is finished, add to result. Right. So we can say something like if well, current size equals length, or but I think we're going to do something different with the crops, so we might not check for empty. Let's say just if the permutation is the size we want, then we're definitely done. So we're just going to add that to the result. And return, right. We don't actually need to have, well, we can have an explicit return here, or we can put the rest of the method as an else. Okay. Otherwise, we're going to iterate over what's going to be next, right? So again, we're going to do a loop over, what did we call it? I don't know, vegetable in, or maybe can we call it next? Maybe not. That might be a reserved word. In crops. So we're going to loop over all the options that we have, and we're just going to say if not current contains that one, then that is a possible next to add, right? And what do we do then? Then we we're going to do, so here's our recursion again. We're going to add the chosen next element, and again recurse, and we're going to pass the same current, the same set of crops. We're going to pass the same length, because that's the target length, not the current length, and result. So that's pretty much it. Okay, so this, as I said, this method, recursive method, doesn't return anything. It just recursively creates all these different permutations, and whenever it gets to the end condition, which is that the length of the current permutation equals the desired length, then we'll add that to our result set. So that means that in order to sort of use this one, I guess we'll do a copy of that, and so what do we need to do here? Oh no, actually we have missed something, right? We missed the undo step. Because we add something here after the recursive call, we have to remove it. We'll come back and do that in let's do that now. So we want to, what can we do? Remove. I guess we'll remove based on index. So we remove the last element, which is current size minus 1. Yeah, there's a remove method that takes an object, but there's also a remove method that takes an integer. So I think that's remove based on index. We should probably look that up. Or is it called something else? Let's look at the API docs. No, wait, it's not in here, it's in YouTube. see. Yeah, so we have a remove for a given index. Right. It does say optional, so I don't know if this will work, but hopefully it will. So we just try to remove by index, so we remove the last element from the list. Okay. Alright, so to use that, we then need to start with an empty permutation. So again, we need a sort of current, which is a, I guess we'll just use an array list of vegetable, which is initially empty, and we need a result set, which is again same as this one. I'm just gonna copy that. And then we're gonna call all perm sub with current crops length and wait, call it perms, something like that, and then return the collected set of permutations. Now I'm just going to comment out this one so that we test the other one, and again we'll test it with sort of length 1, 2, maybe 3, and see what happens. Okay, that did not work. It just gave us an empty permutation. Right, because we can't add current, we have to clone the current. Right, so because we're just passing around a list here and we're modifying the list all the time, then because we're only adding references to the same list that keeps getting modified to the set here. So when we add it to the set, it has a full permutation in it, but then we exit the recursive call and we start removing things and adding things and so on from that same list. So we actually need to clone it if we can. I'm not sure if we can. Can we do that? No, it's okay. So what we might do is something like a new array list. Can we do a copy construct? Let's see if that works. Let's see. There should be a copy constructor in the array list. So we'll try that one again. Okay, so now we get the right answer for length 1. Let's try length 2 and 3 quickly. Quickly. Okay, have we got the right answer for length 2? Yeah, that looks alright. We have 2 of each. Yeah, and we should get the right one for length 3 as well. Yeah, we got 1, 2, 3, 6. Yeah, so that looks alright. Now, if we put length 4 here, this is going to fail, right? In some more or less interesting way, or maybe not. Maybe it won't actually, because we didn't really take care of that case, that special case where the set is empty. But on the other hand, we might not have to. It might actually have sorted itself. No, it didn't. Okay, So this is not completely working, at least if we want it to be sort of robust to mismatched inputs. This works okay as long as the desired length is less than the number of elements, less than or equal, but it will not correctly handle if we ask for something that is longer than the number of elements we have to choose from. But instead of fixing up that, let's just briefly say something about, well, how would we now extend this to a solution to the problem that we actually wanted to solve, right? So remember, the problem we wanted to solve wasn't to generate all possible permutations, it was to generate permutations that satisfy certain rules. Well, the rules as they're written here say that essentially they put restrictions on what can come next. So the structure that we have here in this second implementation is quite convenient for that. Of course, we could have done this with the first one as well. It's just that we choose to add a first instead of a last. But here, because we're picking, in this loop here, we're picking what is going to be next in a sort of unfinished permutation. So if we wanted to actually solve this crop rotation problem, then what we would do here is to do some additional checks. So here we're just checking that the one we're adding is not already in the permutation. That's one of the restrictions. But then here we would do something like check that then can follow last element in current according to the rules, right? So we would do a check here, and if not, then skip it, right? But other than adding that check, this should work pretty much the same to actually solve the problem that we wanted. Right, but we've spent quite a bit of time here talking about recursion, so I wanted to maybe continue and address a few other things that have also come up as questions. So another one is testing, and might not have thought about it, but we saw a little bit of this here, right, already. When we started testing this solution, what was the first thing we did? We tried small values of length, because small values make it easy to verify that the answer is correct. We tried edge cases. We tried 0, we tried 1, or we didn't actually try 0, but at least we were thinking about how to handle 0 when we wrote the code, so we should have tested for 0. So again, let's see, this should work okay for 0. Yeah, so for 0 we get, I don't know, it's a bit hard to say. We should probably put something here like right, let's do that again just to see. We should get a single answer, which is an empty permutation, right, for 0 here. Let's hope we don't get 2. Yeah, okay, so we get a single empty permutation as output, which is what we should get. So we tested edge cases like 0. We did not test with invalid inputs. Now, maybe it's, I don't know if it's actually specified here, but I think we sort of implicitly assumed that the length is going to be a non-negative number, right? It would be rather silly to be asking for permutations of negative length. So even though it's not actually written here, it should be written in the documentation. This should be a non-negative integer. So we didn't test with -1 as input because that doesn't make any sense. So the test cases that we did were things that actually meet the sort of the specification of the method. So what are the other important characteristics? Well, covering the space of inputs and outputs. Well, we can't really say that we covered the space, and of course you will never completely cover the space when you're testing. But at least you should have, if you have sort of different types of inputs and also different types of outputs, then you should have representatives of the different types. So in this particular question, there wasn't really that much difference. We could say that the only variables we have to vary are the sizes, the size of the set and the length of the permutation. So, but in other cases, we might have sort of more distinct variations. Let's say a very typical example would be, or a simple example would be, if you have a method that returns Boolean, right? You should of course make sure that you have test cases that should return true and test cases that should return false. If you're testing for only one of those conditions, then you could have all kinds of errors in your method and you wouldn't know. A way that you can sort of identify what are edge cases or what are sort of that determines coverage is covering branches in the code. So again, in this case, we didn't really have that many special cases or special handling because of the recursive nature. Everything ended up being sort of running through the same branches of the code. Either it's sort of a base case or a recursive case. But let's say if we actually implemented the question that is asked here, so we put these sort of sequence restrictions on our permutation, then maybe things we would do is things like trying a set of vegetables of mixed categories. So here we have a mixed categories, of course. We have 3 of different categories. But also we would test things like, what if we have a set of vegetables that all belong to the same category, or if we have a very unbalanced set of categories, so we have lots of different types of legumes and only one of the other categories, or something like this, right? That's kind of an example of covering the space of inputs in a way that is meaningful for the algorithm. Now, the reason why we're talking about what makes good test cases, well, first of all, because it's one of the pieces of core knowledge that I hope you're taking away from this course, but also because in the sample exams or the past year's exams, you do find questions that are asking you to write test cases. And someone was asking, can we have a look at those kinds of problems and the test cases? So here is another question from the same exam. So this is from semester 1 2020. So this is a fairly sort of big and complicated question. Well, it's not complicated, it's big. And so it's basically to design a data structure, or a class structure and a data structure to represent some information. Right? And in this case, it's saying that this class represents a wiki. So this is a collection of linked articles. And each article has a unique identifier, a name, or title, I guess we call it, a category, and I think it also says, later each article also has a set of editors. So those are the usernames of the people who have edited that article. And articles may link to other articles. each article has at most one link to each other article. So that's just basically telling us that link is going to be a partial relation from article to article or something like this. So to do this, we don't need to keep track of multiple types of links. So it's just either link or no link. So that's the sort of the structure that we want to represent here. If we look a bit further down, what is it we want to do? Well, we want to implement a bunch of methods. The methods that we have here are add a new article, which is then provided all of the information that we need to store about it. Add a link, and here we can see that link is from something to something, right? So links are directional, and we can delete an article. Okay, we have to do that as well. And then I think the rest here is methods that retrieve some information from this data structure. So get the total number of articles, get the get the set of articles that have been edited by a particular user, get all the articles in a given category, get the highest number of incoming links for any articles or any article, and what we got here, get the total number of cross-category links, so that's links from an article to an article in a different category. And finally we have get number of categories edited for a given user. Is that the one? Oh no. And also we have get maximum number of articles in any category. Okay, so we have, I think that's the end of it. Okay, so there's quite a lot of methods to do here. I'm not sure if we want to do all of them. But the second sort of part of this is that we also have this question that is asking us to write some test cases. So it's saying add one or more JUnit tests that test the get max articles in category method. So let's see how we're doing for time. So I don't think we'll have time to actually run through and do an implementation of this question now, but we can at least just sort of look at how would we write test cases for this. I'm not sure if this is such a great method to do test cases for, but right. Do we have to make a slide? No, I don't think we do. We just have to do a void, I guess. What do we call it? I'm not sure what we call it. So, I mean, we just need to remember the JUnit syntax. We put the annotation test on a method, and then that method is something that will be run when we do run JUnit testing, right? And and if I remember correctly, the method doesn't have to return anything. It doesn't have to be static. I think we can actually, you can see the IDE is nice here, and oh no, it doesn't. Does it say that we can run the JUnit on that? Well, if we're not sure, we can just go here and have a look, because here we are provided with test cases for the other methods of the wiki class, right? Or at least some of them. I'm not sure which ones are being tested here. Well, maybe we have to make it public. So a public void, and we annotate it with test. That should be enough. So might have to make it public. I wonder if it says, can we run this with JUnit? No, it doesn't say that. All right. So so what do we do in this one? We're going to do because we're testing this data structure. I guess we will create a new data structure. We'll add some content to it, and then we will call this method and check that the answer is right. So it might look like something like and then we'll do add article, some arguments to that, and then JUnit does we have assertions from JUnit. So in the simple ones, I mean, there's a lot of different assertion forms in JUnit, but really you can get away with just using assert true or maybe assert equals. Unless you want to test for exceptions, then you need to do assert throws and assert not throws. Get max articles in category 0. So I mean, here's our very first test case, right? Which is just we create an empty wiki. Now the maximum number of articles in any category in an empty wiki should be 0. That should be well, that should be pretty much enough. Let's see if we can run that. Maybe we can't actually. It might complain that we haven't implemented the wiki class. I don't know if it's runnable. Oh, maybe it is. Yep, and we even passed the test. So without doing anything. So that's kind of, I guess, a starting point. That's where we might start with that, and then just because of the nature of the question here, because we're testing a method that doesn't take any arguments, the argument to the method is the current content of this wiki data structure. So I guess a reasonable way to be testing this would be that we sort of add articles one at a time, a couple of them, and call this getMax method after every addition and check that we always get the right answer. So let's see. Of course, we're not going to get the right answer because we haven't implemented add, or we haven't implemented getMax either. But at least we can write syntactically correct tests. So we need to provide an ID, a name, a category, and a set of editors. Now, because the editors don't matter at all for this test, we could just provide an empty set. So we might just do a what do we do? A hash set of strings, I guess it is. And I guess we'll be adding some articles. So we'll just number them 0. We'll call that one a category, I think is next. Yeah, okay. And of course, we don't have to really make up anything interesting here. We can just use ABC or something. It's just category is just a string as far as we're concerned, and we'll just pass the same set of editors there. So we start off with just a single article in category A, right? Then now we should have 1 as our max articles in category. Now we have to be a little bit careful here too. Again, this is the first point here about good test cases is very important. If you have assumptions or restrictions on your implementation, then your test cases should satisfy those assumptions or restrictions. So we don't test with nonsense values, right? And in the description here of the wiki class, it says that every article has a unique ID. So I guess since we're providing the ID as an input here, we should make sure that we are providing unique IDs. If we're providing, if we're repeating IDs when we add the articles here, then the implementer of the wiki class should not be held responsible for what happens, because we have clearly said that the IDs have to be unique, right? So we have to provide unique IDs. Actually, we'll call that one something else. I don't think it matters what we put as name, but let's just say we add here, we add 2 more articles in 2 different categories. Now the maximum in any category should still be 1, right? Because there's only 1 article in each category. And then I suppose we can go on and sort of add a few more. Let's say we add another couple of articles to categories B and C. Let's just add 1 to B. So then this should have changed to 2. And then if we add another 1 to C, then it should still be 2. So 2. And maybe if we then remove, do we have a remove or delete? Delete article. So if we delete, let's say if we delete article 0, which is the only one in category A, well then the answer should still be 2. If we delete article 1, let's say, well, the answer should still be 2, because there should still be 2 in category C. And then if we delete article 2, then I think if I calculated right, the answer should then drop to 1, right? Yeah, so something like that might be sufficient testing for this method of this particular class. All right. So, unfortunately, that sort of brings us to the end of our scheduled time. We do have a few more things that we could talk about. We have heaps of things we could talk about. But I think we're going to run up against the recording finishing in a minute. So I think we'll deal with other questions on Piazza, and then, as I said, if there is sort of wide interest, we might run another revision lecture on Friday as well, since this one ended up being quite long. Just any last questions about the content we covered today, or about the exam, or anything else at the moment? Probably not. Like if it's typically if it's something that is not running at all, or like not compiling, then probably not. It depends a little bit on the question. So, for example, for this test case question, you might get, or let's say for this question 3, which had really 2 parts, you could probably get marks for the test cases even if you had a broken implementation of the wiki class.